Welcome to Intellipaat's YouTube channel. In today's video, we will be learning about union, linked list, tree and sorting in data structure. But before we begin the session, make sure to subscribe to our channel and also hit on the bell icon so that you will never miss an update from us.
Let's start with structures. So what is a structure? A structure is a user-defined data type, which is collection of different data types to store a particular type of record. So assume it is a collection of the already defined data types. For example, if you want to have your own data type which has one integer, one character, one float to perform some operation, then structure is an answer to your question. I will give you one more example. For example, you want to maintain a student record of a school where each record contains a student name and student age and student roll number, etc. So we can solve this problem by using structure, where we can define our own data type called student record, and each record will have name, age and roll number, and so that we can work based on the data. Let's continue. To access a structure member in C, structure variable should be declared. So we should declare a structure variable. We'll see how to do that. Many structure variables can be declared for same structure, and memory will be allocated to each separately. So we just need to define a structure that we will be using this structure, and we can use n number of structure variables, and the memory for each structure variable will be allocated separately. And also it is a best practice to initialize a structure to null while declaring if not assigned any value to the structure member. So if we are not using any structure variable, it's always good to initialize it by null so that it won't be having any garbage value. So what is the difference between structure and array? The difference between structure and array is that array is used to store a collection of similar data types. So I can have a array of 10 integers, but all the 10 elements should be integers. While structure can store collection of any data type. So I can have one integer, one float, one character, one long, one double, and so on. I can have multiple integers, multiple floats. So it's up to us how we define how we can have how we want to define our structure. So that is how that there is a difference in structure and array. So array stores similar type of data or same data type. Structure can store different data types or whatever we want. So declaring a structure keyword is used to define a struct keyword. This is a keyword that is used to define a structure. It is a data type which is a collection of different data types. So struct is nothing but a collection of different data types. So here is example. It's a struct, okay, structure name and data type and variable name, data type variable. So data type could be int, char, long, float. The structure will be referenced by this name, structure name. Structure variable declared using normal variable as structure name. So if you want to use a structure or want to declare a structure, we have to use this name. We have to use this name to declare the variable structure variables. So this is the example. This is a structure of a student record. So this is our user defined structure. So this structure has integer which is saying marks. This structure also has a character array which says name and a float which says average. So this is a structure, and how we can define a structure or how we can declare a structure in our program is like struct student and report. So this is our variable name and this is the data type. Initializing and accessing structure variables. So let's see how we can do that. So there are here we are touching upon two types of structure. Two types. Like one is a normal structure, which is a normal variable. One is a pointer variable. So let's see how the de- uh, normal variable or normal structure variable is used. So report equal to, this is how we can initialize 100 AVI 99.5. So this is 100 is mark or marks, whatever we can say. AVI is the name and 99.5 is the average. If you want to use a pointer, we can do it like this. At this point of time, you can ignore it, but if we declare it like this, then this variable will be storing the address of structure. So just say that there is some address associated with the structure, and pointers stores the address. So accessing is using normal variable. So how we can access the data? If you want to check marks, then you can say report.mark. If you want to get a name, then you can say report.name. If you want to say if you want to get average, then you can say report.average. To access the entities inside structure in using pointer variable, you need to have you need to use special type of operator, which is called an arrow operator, and we can use like rep arrow mark, rep arrow name, and like this we can use. In this session, we are mostly touching upon normal variables. Will not be uh, using any pointer variable. So array of structure. This is a very basic code of how we can use the array of structure. So let's go through the code. First, I am declaring or I am including our preprocessors, and so here I am including stdio.h and string.h. This is how I am defining my structure. So structure is having integer, character, and float. So in integer ID, I can store anything. I can store roll number or student number or whatever I want. Uh, in this, I can store character array. So this could be very feasible to store names. Floating variables say percentage. So what is the percentage student? Percentage marks in the last subject, or average marks in all subjects. So that we can take. Let's see how we use it in main function. So integer I, now we declared a structure array struct student. So struct student, struct says it's a structure, it's a student type of structure, and this is a variable name. Okay, and this is of the variable is of type array, and the size is 2. Okay, now in the first position, like record 0 dot id, so this is the first structure. We'll be initializing it as 1, and then copying abc into that name, percentage as 86.5. Second element of the structure, id equal to 2, name equal name, we are copying it with xyz, and percentage with 90.5. So this is how we can use structure array. We can use loops also, or we can use n number of types of n number of ways of using arrays. So passing a structure in a functions. Structure can also be passed in a function, and we can use the structure in that function. So let's see how we can do that. Consider this example. So we are having this structure, same structure, and id, character name, and float percentage. Now we have a function, void function, which accepts a structure. So struct structure of type student, variable name is record. Okay, so now how we are using this structure in a function is we are just doing printf. Okay, so let's suppose we want to have we have declared a lot of structure, or structure is having lot of variables, and we want to print the structure. So we can declare a function that can print the value of structure. Let's see the main function. In main function we have declared one structure, struct student record, record.id equal to 1. We are copying abc into the name. Percentage we are making it as 86.5. Then we are calling this function. Once we call this function, the control goes here and it will start printing the data inside the structure. So what will be the output of the function, output of the program? The output is of the program is this, whatever is printed by the function func. So the output is id is whatever we have given the id. Say id is 1, name is abc, percentage is 86.5. So this will be the output of our program. Nested structure. So we can have structure inside a structure. That is like, suppose our demand is to have very complicated structure like this, where we have student record. In student record we have student name, student age, and then we have a student address. So again, address is another type of structure. So we can declare address as the locality, which city, pin code, and also it is normal, or it depends upon how our, what is the problem that we want to solve. Do we want to have a nested structure or not? So if you want to declare, or if you want to use a nested structure, we can use like this. So if you want to access the locality, what we have to do is, whatever variable we have declared, for example, we have declared struct student um, abc. Okay, then if you want to address check the locality, how we can do is abc dot address dot locality. So this is how we can check. Let's move ahead. When we talk in uh, structure point of view, so typedef is a keyword used to assign alternative name to existing types. So if you want to give a some name to our structure, or some alias to our structure, typedef can help us out. It is very common when while using the structures, because defining a structure is a very like, you need to write a lot of characters. First you need to write struct, then what type of structure it is, and then the variable name. If we declare a type def, like if we declare an alias to the structure, then we can remove the dependency on writing struct and the type of structure. We can just use the alias and variable name. So let's see how to use the type def. Here we are using type def. Again, I'm including the preprocessors. Then type def. Okay, I'm defining or aliasing this structure. So type def struct employee. I'm declaring a structure of type employee. Employee is having a name and a salary, and I'm making the alias as emp. Now in the main function, how I can use is emp e1. So emp is nothing but struct employee. So instead of writing struct employee again and again, it is easier to write emp e1, and it is easier to refer this in our program and read it in our program. So emp is nothing but an alias to our alias to this structure, and this only helps in declaration part. Usage part will remain the same. So what is union? Union is also similar to structure. It is a collection of different data types which is grouped together. Each element in union is called a member. So anything inside a union is called a member of union. Okay, so union allocates one common storage space for all its member. Uh, as compared to structure allocates memory for its member or for the entities separately. So uh, what how number of entities inside the structure is, so the size of the structure depends upon the number of entities inside the structure. But in union, the size of union is dependent upon the biggest member inside the union. So suppose we have declared two members inside union. One is say int, another is say float. So the size of the structure will be equal to the size of float. Sorry, size of union will be equal to size of float. So that's how we use union. We can access only one member of union at a time because union allocates one common storage space for all its members. Many union variables are created in a program and memory will be allocated for each union member. Union variable separately. So yes, we can use many variables of union, but for each union, the size of memory is equal to the biggest member in the union. So this is the example that we use in the union. So union is again same. It is almost similar as declaring a structure. Instead of struct, we use union. Okay. Then we declare two variable, record one, record two. So then we are copying name and name and subject inside the record one percentage equal to 86.5. Okay, union values example. Then again we are printing it. Okay, now we are again initializing or printing the name as record two dot name, copying a subject, printing a subject, and then assigning a percentage to record two and then printing it. So what will be the output of the program? The output of the program will be something like this. One correction is the subject will come here, physics. Okay. So this is the difference between structure and union. Structure allocates storage space for all its members separately, whereas union has a common storage space which is equal to the biggest member of the union. Structure occupies more memory space, union occupies less memory space, obviously, because structure allocates storage space for all its members, union allocates memory space for only one member. All members of structure are accessible at a time, but in union only one member is accessible at a time. This is because again related to memory, where structure can allocate memory to all its member, but union cannot do that. That's why we can access only one element at a time in union. So this is how we declare structure and this is how we declare union. So memory allocation of for the above example. So how much memory will be allocated? Int will give 2 bytes, character we are using 6 character to, so 6 bytes, so 6 plus 2 8 bytes. For the above case where we are using union, it will be equal to the 6 bytes because 6 bytes is the biggest unit. We will be writing a very simple program to input records of a student and then we'll be printing it accordingly. So let's assume what all parameters or what all things does a student record have. A student record contains student name, student age, student roll number, and etc. So we will be considering only these three parameters. We'll be taking input from user and then printing it accordingly, uh, so that it can be displayed in a user visible manner. Uh, with this example, you will be getting more hands-on practice on how to use structures, and in further sessions, which is followed by which we will be using in data structures and all, we will be using structures a lot. So this will help you in getting more and more understanding on structures. So let's get started. So let's create a file for this program. Let me create a student record.c. Okay, hash include. We have a max value. The max value will be defining how many number of records do we want to have. This will be our counter. Uh, so before that, we have to define a structure. So uh, how the structure will be, let's define it. Struct student. Okay, so name, let's say it has 20 characters max, then age, roll number. Okay, so let's use this structure. Let's define an array of structure. Struct student, say s. I'm defining it as uh, number of array elements is equal to whatever is declared in max. So it will be like this. Now let me run a loop. Equal to 0, I less than max, I plus plus, printf, enter. Scanf percentage s of I dot name. Here we are referring the ith index of this array and the name attribute. Okay, scanf d ampersand of s of I printf roll number of scanf percentage d ampersand s of I. At ith position we will be getting roll number. Okay, so this way we'll be getting we'll be initializing the array of structures with the given input by user. Now let's write a loop again to print all the values. Max, I plus plus. Okay, So here we'll be giving printf name will be %s, age will be %d, roll number will be %d, and then we'll be printing dot roll number. Okay, so that we'll be printing in a clear format. Okay, so this is a very simple program to demonstrate how to use the structure. So let's try to compile and run the program. So the program is compiled successfully. Let's run it. So enter the name of student. Say I'm giving only one character. You can give up to 20 characters. Enter the age of student. Let's 21. Enter the roll number. Say 20. Say 1. Okay. So one record is here. The one record is completed. Okay. Now this starts printing the second record. So enter the name of student. You can give anything. Enter the name of student. Enter age. Enter the name of student, age, age, roll number, again, age, roll number, again, name, number. So at this position we have completed our uh, process of getting the input from user, and here we are printing all the records, all the student records. So we can perform any type of operation on the set of records. Here I am just printing it in a user readable format, a kind of a tabular format like this, where name, age, and roll number are displayed like this. I'll recommend you to try this example on your own and try multiple variants. Uh, do some do some logic around whatever how whatever you want. Like for example, you can sort the records based on the age, or you can sort the record based on the name, or you can print the record in a reverse order, or find a record where uh, name of the student starts with A, and find the record where age of the student is greater than 20, or something like that. So it's up to you. The mm, you can try any combination of this problem, and uh, only by trying this problem you can get more and more understanding on how to use structures and all. So I hope this problem or this example is good enough to uh, make sure that you have a basic understanding of structures. So what is a linked list? A linked list consists of a sequence of nodes. So what is nodes? Node is a segment of memory. Uh, so here this is a segment, memory segment, this is a memory segment, this is a memory segment. So linked list is a sequence of node. Node is a section of memory. Each node contains a value. So every node has a value. and a link which is pointing to some other node. So this is the link part which is pointing to some other node. So that is why it is called a linked list, because each memory section is linked to some other memory section. So it's a chain that is being built upon, and the last node will contain a null. So this is how our chain terminates. So let's reiterate. Each node in a linked list has two sections. One is a data section, one is a link section. Uh, each link points to some other node, and which constitutes the chain, and uh, that is why it is called linked list, because there is a link between one node to another node, and it's a linear format, so it is called a list. So linked list. So the list may have a header. uh, it's good to have a header. Header is nothing but it says that from where my linked list is starting. So generally it contains the location of your first node. So here is a starting element of the linked list, or I can say the head of the linked list, which contains the memory address of the first node. So this is the linked list. This contains the first address of the first node. Then node A has B as the next node, B has C as the next node, C has D as the next node. So what is the terminology that we used in linked list? A node's successor is the next node in the sequence. So the next node in the sequence, this is the successor of uh, the node. So B is the successor of A, C is the successor of B, and so on. The predecessor is the previous node of the sequence. So A is the predecessor of B, B is the predecessor of C. The list length is the number of elements in the list. So in this linked list we have 4 nodes, 1, 2, 3, 4. So the length of the linked list is 4. So this is what we used to call or we frequently use these words in the linked list. So let's touch upon how to create a linked list. So let's assume this is a linked list. Linked list has, as we have covered, that this is a memory segment which is also called node. Each node is a structure uh, which has a value and a pointer to the next node. The pointer to the next node is nothing but a pointer to the same structure. Uh, the data part, or the value part, whatever we call it, here we are using an int value, but it could be anything. It could be another structure, it could be another string, character array, it could be anything. So whatever we store here is a data, which could be anything. Here we are using integer. Whatever we store here is a pointer to another structure which stores the address of the next node. So this is how we define a node. Uh, to assign a memory to a structure, we have to use malloc. So this is how we assign a memory to the structure. Initially, when we declare any structure, it won't be assigned any memory. So we need to allocate some memory to the structure. So this is how we do that. Then once the memory is allocated, how we access the value part of the linked list is temp, and this operator arrow, this we call as arrow operator, which is nothing but hyphen and a right arrow. So this is called an arrow operator, and temp arrow value. So temp arrow value will help me to access the value portion of the node, and we can store the value like this. So this is how we can assign the value. Okay, this is how we can access the next element of the, or the link part, or the next part of the linked list. We can assign it to some other node, or we can assign it to null. Okay, so struct node my list equal to temp. So here what we did is we created one node, one empty node, and then we assigned the root. This root will be pointing to temp. So temp will become our first node. Let's learn about traversing the linked list. So traversing the linked list is nothing but going through the linked list in a way how we, as and when we get the address of the next part. So for example, we have declared a structure like this, which has in data part as an integer and a next part. Then this is a root element, and then we generally will take a temporary variable which is and we assign it to a root, and then we run a loop which continues until temp is not equal to null. We print the data like temp equal to, temp arrow data, and temp is assigned to the next element. So temp will be keep on increasing, keep on increasing, keep on increasing, and until and unless temp becomes the null, or because at one point of the time, if we have a terminating linked list, like the last element of the linked list is pointing to null, so at one point of the time we will be hitting that pointer, and we'll be getting null. So this loop will end, and we'll end up traversing entire linked list. So let's see how we traverse a linked list. Say this is our linked list. This is a data part, this is a link part. So suppose we have declared a temporary variable this. Now initially we assign temporary variable with a root which will point to here. Then once we print this, we assign uh, this dot next, which is this, to the temporary variable. Now it will point to here. Again, the next part is assigned to the temporary variable, which points to this part, and again finally we end up getting a null. So this is how we traverse a linked list. So let's touch upon what all are the operations which are possible in the linked list. So there are two operations which are possible in the linked list. One is insertion in the linked list, one is deletion in the linked list. So insertion and deletion could have many flavors. One could be inserting at the end of the linked list, one could be inserting at the beginning of the linked list, one could be inserting at the middle of the linked list. Similarly, deletion could have many flavors, like deleting the last node of the linked list, deleting the first node of the linked list, deleting something in the middle of the linked list, and so on. So we have different flavors of insertion and deletion. So this is we are explaining more about insertion. There are many ways to, you might want to insert a new node in the linked list. Insert as a first element, insert as a last element, insert in the middle. How you do insertion in the middle, like before a given element, after a given node, before a given value, after a given value. So there are many combinations that we can try out on insertion. So all are possible, but it depends upon what operation we choose, and each operation has its own difficulty level.
Just a quick info, guys. Intellipaat provides C and data structure training mentored by industry experts, the course link of which is given in the description below. Now, let's continue with the session.
For example, adding a node at the end of the linked list is easy. Adding a node at the middle of the linked list is a bit trickier. So it has each and every operation or each and every flavor of insertion in the linked list has a difficulty associated with it. So inserting after, how does this function works? Inserting after. So let's suppose we have this linked list and we want to insert a node 2.5. So find the node that you want to insert after. So let's suppose we insert our node after 2. So here we want to insert after 2. First copy the link from the node that's already in the list. So you need to copy this link somewhere. Okay, so what we will do is 2.next equal to node.next and node.next. So what will happen is this 2.next will point to 3, node.next will also point to 3. Now we will have to do, we will have to make 2.next points to node. Change the link in the node that's already in the list. So we need to change the link of this to this. First we have to dereference it and assign it again. So this is how we can insert the linked list. So now when we traverse the linked list, it will be like this element, then this element, then this element, then this element. So let's do some practical example. Let's write some code for this. So this is the code for very basic operation of inserting into the linked list and traversing through the linked list. Here we have declared a structure of node. The data part is integer. The next, or the pointer which is pointing to the next node, is next. Then we have a declared two function add, which adds a value to the linked list, and then we have a function called print, which prints the entire linked list. So let's go to these functions, add and print, then we come to main. So first go with the add function. This is our add function. So what we are doing is we are passing a pointer or we are passing the address of the root element, root or head, whatever we call it. Then we are passing the value what we want to store in the new node. So here we are adding a node at the end of the linked list. Just for simplicity, we are doing this operation. So now what we are doing is we are having a temporary node and assigning a memory to it. So we are allocating some memory to a temporary node. The node type should be struct node temp. Then we will be filling the data inside the node. Temp.data equal to value, temp.next equal to null. So why we are making temp.next equal to null? Because we are adding the node at the end of the linked list. So we want this node to be a terminating node. So that's why the next element should be null. Okay, now we are doing some checking, like if our root is null, if value at address root is null, that means our head or root or starting point of the linked list is null, that means our linked list is entirely empty. Then what it will do, it will assign value at address root equal to temp. So temp will be stored at the root, or root will be pointing to the temp. So this is the creation of first node of linked list. Now in case we already have something in the linked list, then what we are doing is we are declaring some temporary variable called list and assigning it to our root. Then we are traversing like this. If list.next is not equal to null, we are assigning until and unless we get some node whose next is null. Okay, once we find that node, what we are doing is we are making list.next equal to temp. So the last element of the existing list will point to the temporary element or temporary node, and in temporary node we already have the next part pointing to the null, so ultimately we end up adding the new element at the end of the linked list. So this is how we traverse the linked list. This is a function called print. It is accepting a root a root pointer. So struct node, we are declaring a temporary variable here. Then while temporary variable is not equal to null, we are keep on printing the data at the node temp. So we are printing temp dot data and incrementing temp equal to temp dot next. So we are assigning we are jumping from one node to another, one node to another. So how the jumping works like this: temp equal to temp dot next. So until and unless temp becomes null, this loop will continue and we'll exit out of the loop. So how we use this into the main function? Okay, this is the main function. We have declared struct root equal to null. So initially we have declared a root of our linked list and initialize it with the null value. That means our linked list is entirely empty. Now what I'm doing is I'm declaring a variable I which is used for loop. I'm running a loop from 0 to 10 or 0 to 9 and adding I to the linked list. So I am adding 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to the linked list. Then what I am doing, I am printing the linked list. So this is here I am adding elements 10 times in the linked list, one after the other, and here I am printing the entire linked list. So let's see how this program runs. GCC -o linked list.c. So I got a compilation success. Now /linked list. So if I run this program, what I am doing is I'm initially the nodes are getting added and then we are printing. So output of this program is we are printing the linked list. So this is how linked list will behave. Okay. So let's see one more program which is another flavor of adding the value or adding the node in the linked list. So here I am continuing with the existing program that we have discussed just now, and I am adding one more function called add after. So what this function will do, it will add a node after this value. So it will search for this value and add a node which has the data part as this value. Okay, so let's see this function, how this function behaves. Add after, this is a function add after. So I am adding value after x. Okay, so initially we are checking if root is null, that means our linked list is empty, so we don't have anything to add. We'll return safely. Say struct node temp equal to root, we just have a temporary node which is pointing to the root. Now then we are running a loop to find the value x. Okay, so we are doing two things. We are doing temp equal to temp dot next. That means we are jumping from one node to another node until we find null or we find x. Okay, so here is the jumping part, temp equal to temp dot next. Then once we exit out of the loop, we'll check if temp dot next is not equal to null. That means once that means it is we arrived at a point where it is not the last element of the linked list or last node of the linked list. If this is the case, that means we are adding the node in between. We are declaring a temporary struct node p and allocating a memory to it. Then what we are doing is p dot data equal to value, p dot next equal to temp dot next. Okay, so p will p uh, the next element that will come after p will be temp dot next, and then we are assigning temp dot next equal to p. So temp will point to p and p will point to whatever the temp was pointing earlier. So we have added p in between temp and temp dot next. So that's how add after works. Let's see how we use it in the main function. So this is the part which we have covered earlier. So we have declared a root, we have added 10 elements, we printed the linked list. Now what we are doing is we are adding a value called 34 after 4. Okay, and then we are printing the linked list again. So let's compile and run this program. So we got a compilation success. I named this program as linklist1.c. You can name it with anything you want. So here is the output. This is the first print that we did. Like this is a normal linked list, or linked list where we have added the value from 0 to 9, and then I have added 34 after 4. So here what we got the value 0 1 2 3 4, then 34, then 5. Like earlier it was 4 is pointing to 5. Now what is happening, 4 is pointing to 34 and 34 is pointing to 5. So we have added after the particular value, or we have added one node between the two nodes of the linked list. So let's see how deletion works. So in order to delete a node from a single linked list, you have to change the link of its predecessor. So uh, predecessor means whatever node which is before a particular node has to point to the node which will come after the node that we are deleting. So little bit confusing, but suppose there is three nodes A, B and C. A is pointing to B, B is pointing to C. Uh, so we have in this case, if we want to delete B, so what we need to do, we need to change the link of A. That means the next portion of A. So A should point to whatever B is pointing to. So now in this case B is pointing to C. So to delete B and maintain the linked list, A should point to C. So this is what we are going to say, the predecessor should point to the next element of the current node. It is slightly tricky because you can't follow a pointer backwards. So deleting the first node in a linked list is a special case because the node's predecessor is the list header. So let's revisit these 2 points. Why deletion is tricky? Because you don't have a pointer to the previous node since it is a singly linked list. There is a cases where we have a pointer to the previous node where we call it, where we have a doubly linked list, which we will cover later. But talking in terms of singly linked list, it is difficult to delete a node in between. So we need to write some logic so that we can have a predecessor's pointer, so that we can manipulate the predecessor's next portion to point to the successor's next portion. Okay, so let's write some code for deleting the node in the linked list. This is the code for deleting the node in the linked list. I have followed the first program that we have written. So we have two methods, add and print. Why we require these two methods is because we need some data in the linked list, so we have these two functions. The new part is this: I have added this function delete node. So what delete node will do is it will delete a node uh, which has value equal to VAL or whatever we will provide in the as a parameter. So let's see this function. So delete node, this is the function delete node. So what we are doing in delete node is we are maintaining two pointers, one is temp and one is previous. Okay, temp will point to will be assigned to root. Previous is we set previous equal to null. Then what we are doing is we are running a loop to find a node which has value or data portion as equal to val, and similarly we are jumping temp equal to temp dot next, and what we are doing is we are jumping the previous also. So what we are doing is previous is assigned to temp and temp will assign to temp dot next. So we are maintaining two pointers and we are moving two pointers. So we are maintaining a link to a predecessor and we are maintaining link to a successor. So if previous equal to null, then return. That means we don't find anything like our loop is ended and we didn't find anything. So uh, we return safely because there is nothing to delete. If temp dot data is not equal to val, like we found, we our loop is ended, but the pointer which is pointing to temp does the data portion does not match with the value. So that means we reached to the end of the linked list, but we didn't find anything which is matching to value. So again we return safely. If none of the condition matches, then what we do is we make previous dot next. That means predecessor next pointer equal to successor's next pointer. So predecessor dot next will point to successor dot next, and then we will free the memory. So we now temp dot next is will be pointed by previous dot next. So there is no, and we need to delete the temp because temp dot value is equal to whatever value we want to have. So we can free the memory. So that's how we delete it. So let's go through the main function, like how we are using it. So in main function again, what I'm doing is initializing the uh, our linked list from 0 to 10 or 0 to 9, printing the linked list. Then what I'm doing is I'm deleting a node 5 and then again reprinting the linked list. So let's see what happens. Let's run the code. C minus linked list 2. So we got a comparison success. So here this is the output. So this portion here, this is the first print where we have initialized the linked list and did a print. Now this is the print after we have deleted the nodes. So you can see we have deleted 5 here and 5 is not coming to picture. Earlier 4 is pointing to 5 and 5 is pointing to 6. Now 4 is directly pointing to 6 and we have freed the memory which is holding 5. So this is how we perform deletion in the linked list. Okay, so this is a small animation. To delete the first element, change the link in the header. So if you want to delete the first element of the linked list, our header should point to the successor of the first node. So this is the this is the linked list, and we remove the link, or we this variable does not point to this, but it points to this. So this is now our linked list will be like this. We will not be using this, and we can free this memory. To delete some other element, change the link in its predecessor. So like this is the predecessor. So predecessor will not point to this. Suppose we are deleting this node, so predecessor will not point to this, but it will point to this. So this is how we traverse the linked list now, and we can free this memory. Delete node will eventually be a garbage collected, or we need to free the memory so that uh, we don't overuse the memory. If we are not freeing it, it will be held up and will not be it's a memory loss. Okay, so let's touch upon what is a doubly linked list. So doubly linked list is nothing but an extension to a single linked list, where each node will be having two pointers. One is pointing to the predecessor and one is pointing to the successor. So here this is suppose consider this node. So this node has now three portions. This is a data portion, this is the next portion which is point to the successor, this has one more portion which points to the predecessor. uh, so accordingly we will make changes in the structure. And how the doubly linked list will help, like in case of deletion we need to maintain two pointers. Now in this case where we have doubly linked list, and if you want to delete anything, we don't need to maintain two pointers. We just find the value which we need to delete, and then go. Suppose we want to delete b, we find b, and then we go to this element a. Then what we'll do, a dot next will point to c, and c dot previous will point to a. So that's how we can do. It's a very simple thing. So each node contains a value, a link to its successor and a link to its predecessor. The header points to the first node and in the list, and to the last node of the list. Uh, so header has two information. It depends upon how we build a linked list. It is not always mandatory that header should have information about the last node. Uh, it all depends upon our execution, like how we want to maintain. So it's up to us how we write a program, whether we want to maintain the pointer to the first element only, or we only need to maintain two pointers, one which point to the first element, one which point to the last element. So DLLs compared to SLLs. So before that, let's write some code for the doubly linked list. So this is the code for doubly linked list. So as you can see, we have a structure node. Earlier it was having data and next pointer. Now it has a previous pointer also, which points to the predecessor of the node. This points to the successor of the node. Then what we are doing is, while we need to modify add and print function, all not print function, but we need to modify add function also. So let's see how the new add function will look like. So this is how our new add function will look like. Again, here we are just initializing the memory. Now the temp dot data equal to value, temp dot next equal to null, temp dot previous equal to null. So here we are just keeping initializing a node which with the default values. Then we are finding if root is equal to null, that means it's an empty linked list. We are assigning root equal to temp. In case our linked list is not empty, we are having a temporary pointer and finding the and traversing till we reach the end of the linked list. And then what we are doing is temp dot previous equal to list. That means temp dot previous, like predecessor of temp will point to the this variable list, and list dot next points to the temp. So that's how we add it. And we have also written one function called print reverse, which prints the linked list in the reverse order. So let's see how this code is. So this is a print reverse function. What it will do is, it will just uh, we pass a root to this element, to this function as a parameter. Then we have a variable which points to the root. So first we go to the end of the end of the linked list. Now here in this w linked list, we are not maintaining a pointer which points to the end element of the linked list. So if you maintain that pointer, then you need not have to do this step. So since we are not maintaining, we need to find the end of the linked list, and from the end we are jumping backwards and printing the value. So printing the value, jumping backwards, printing the value, jumping backwards until temp is equal to null. So this is how we do operations in W linked list. I'll suggest you try this and do some modifications, like add some element in the W linked list, delete some nodes in the W linked list, and have two pointers which points to start or the first node of the linked list, and one points to the end of the linked list, and do some operations uh, like add the values in the linked list and print the sum and do all kind of things operation. There are number of operations possible in linked list. So let's compare doubly linked list and singly linked list. So DLLs start for doubly linked list. Doubly linked list is short form of doubly linked list. SLL stands for singly linked list. SLL, singly linked list. So singly linked list is nothing but what we have discussed before doubly linked list, where any node points to the successor. It does not have a predecessor node. Okay, so advantages, uh, can be traversed in either direction. So doubly linked list we can traverse in either direction, front and back, uh, but we cannot traverse in uh, from any direction front and we cannot traverse in back direction in a singly linked list. Some operations such as deletion and insertion before a node becomes easier. So in a doubly linked list, it is easier to perform operations like add some node at the middle of the linked list and delete some node at the middle of the linked list. In the singly linked list, we need to maintain uh, two pointers, which one points to the predecessor, one points to the successor, and then we need to do some operations. So in doubly linked list it is much easier. Singly linked list we need to write some extra code. So what are the disadvantages of this thing? So DLL or doubly linked list requires more space, because now in doubly linked list each node has an extra link which is linked to its predecessor, so it requires extra memory. List manipulations are slower because more links must be changed. So if we want to do some manipulations or want to change links in bulk, this is tedious operation. So greater chances of having bug because more links must be manipulated. So if we perform this operation where we need to change most of the nodes in bulk, it may happen that we end up in some bugs which is not easy to debug. So we need to be very sure what is our requirement, and do we really need doubly linked list? Can we do operation with singly linked list? What is our performance impact in with the time complexity and memory complexity? So we should take care of these stuff before deciding what to use. So deletion a node from a doubly linked list. So node deletion from doubly linked list involves changing two links. In this example, we will delete node B. So earlier example we have set of three nodes A, B, C. Now in this example we are deleting a node B. So this is our linked list. We are deleting node B. So what we are doing is the link uh, the A's next link which is pointing to B is removed. Now A is pointing to C. C's previous which is pointing to B is removed. C's previous is now pointing to A, and that's how we delete it. So we don't have to do anything about the links for the B, and we can free the memory. Garbage collection will take care of deleted nodes. So we need to free the memory, and then it will be taken by the garbage collector. Deletion of the first node or last node is a special case. So if you want to delete the first node, then what we need to do is this node will point to this, and the previous of this will point to null or nothing. So we need to change the things, and similarly if we want to delete the last node, we need to adjust the pointers accordingly. So other operations that are possible in linked list are like most algorithms in linked list, such as insertion, deletion, and searching are pretty obvious. So you just need to be careful what linked list you want to choose and what operations are required in your program. Sorting a linked list is just messy since you can't directly access the nth elements. You have to count your ways through the lot of other elements. So if you want to sort a linked list, it requires some effort because we cannot directly access the uh, element through index as we can do it in array. We need to traverse through the linked list, find the element, and do the changes. And also we cannot shuffle the value very easily. For example, we can shuffle two values in array very easily, but if you want to shuffle two values, we need to change a lot of pointers. So we need to be very careful in that also. So there is a special case called circular linked list. Circular linked list is nothing but it has one head element, and it has uh, other elements like as usual, and the last element, the next portion of the last element or the successor of the last element is the first element. So while traversing the linked list, what we have to do is we just have to say where is my head, and we find the head, then we traverse like this 2 5 7 8 10. Now 10 points to 2 again, so this is, we will be revolving in a circular manner, so that's why it is called circular linked list. So circular linked lists are also very known data structure in computer science, and these are used for developing circular buffers and all. So but we need to be very careful while using circular linked list, because we might end up in an infinite loop, because there is no terminating condition here, because there is none of the node is pointing to null. So if we keep on traversing a linked list, and we need to set proper conditions before our loop get terminated, so we need to be very careful in that. So what is a binary tree? A binary tree is a composed of zero or more nodes. In C, reference to a binary tree may be null. So binary tree is something like this. So any node has two references. So suppose this is a node, okay. uh, this node has two references. One is the reference to left part, one is a reference to write part, and this is a data section. Okay, so binary tree is composed of two or more nodes. Here we are having two nodes. One is for left reference, one is for right reference. Okay, each node contains a value, a reference or a pointer to left child, a reference a pointer to right child. So whatever be the reference that it has towards its left, this is called the left child of this node. Whatever the reference this node has towards the right, so this is called the right child of this node. Okay, and if any node is there with no reference, then it is called as the root node. Okay, so we always start with root in the binary tree. Then each node in the binary tree has two references, one is left, one is right, and we keep on building the tree. A binary tree may be empty, so in case if binary tree is empty, then this node will be null. So if root is null, that means binary tree is empty. If not empty, a binary tree has a root node. So if not empty, this will have some value, and whatever value it has, this will be called as a root node. Every node in binary tree is reachable from root node by a unique path. So every node in a binary tree can be accessed by root node through some unique path. For example, if you want to go to H from root, the only path you can go from here, root to H, that means A to H, is you need to go from A to B, B to E, and E to H. There is no other path that you can go from A to H. There is a unique path from root to every node. A node with no left child and with no right child is called a leaf node. So suppose there are any nodes with no left child and no right child, for example like this. So it does not have anything on the left, does not have anything on the right, so this is called a leaf node. Okay, so in binary tree what all we have a root node which does not have any reference upwards. Okay, and then for any node we have a left reference and right reference. The left reference is called the left subtree, right reference is called the right subtree. There is a unique path from each node from root. So if you want to go from root to any node, there is only one path, and if any node which does not have any left reference or right reference, then it is a leaf node. So this is a very basic binary tree representation, and as and when we proceed, you will be able to understand these concepts more and more in depth, and this will give you more understanding on what are binary trees. Okay, so let's continue with further explanation on binary trees. So in binary tree, the following two binary trees are different. So suppose this is a node and this is one more node. Both node has same values a and b, but these two are different binary trees. Why? Because here in this case b is the left child of a. Okay, but in this case b is the right child of a. So the representation of a tree in this diagram and representation of tree in this diagram is totally different. So hence we call it as a different binary tree. If the first binary tree node a has left child but no right child, correct? So it has left child but no right child. In second node a has right child but no left child. Put in another way, left and right are not relative terms. Yeah, so left and right are not relative terms. You cannot just do some relation between left and right. So binary tree terminologies. Node A is the parent of node B if node B is the child of node A. So what is mean by parent and child? In this case, node B is child of node A. That means in hierarchy, node A comes first and node B comes after A. So A is parent of B and B is child of A. Node A is ancestor of B if A is a parent of B. So
Just a quick info, guys. Intellipaat provides C and data structure training mentored by industry experts, the course link of which is given in the description below. Now, let's continue with the session.
another thing is also called as node A is the ancestor of B. So whichever comes first from the traveling from the root will be the ancestor of the node which comes after that node. So A comes first and B comes after A, hence A is the ancestor of B. Node B is a descendant of A. So similarly, B comes after A. So B is the descendant of A. Node A and B are siblings if they have same parent. So if A and B are having a same parent, like suppose there is a node called C here. Okay, let's say C is here, then B and C will be siblings because B and C will have same parent called A. So let's cover about what do you mean by size and depth of a binary tree. So suppose this is a binary tree. The size is the number of nodes in a binary tree. So here in this case, number of nodes are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the size of binary tree is 12. Correct. The depth of the binary tree is the node to its distance from the root. So A is at depth 0. So because since A is the root, so distance from root to root is 0. B is at distance 1. C is also at distance 1. E is at distance 2. H is at distance 3. So E is at depth 2. 0, 1, 2. This is the second depth. Also you can say number of hops that you need to do while reaching from to a particular node from A or root. So if you want to reach E, how many hops you have to do? 1 and 2. So 2 hops you need to do. So number of hops equal to the depth of a particular node. The depth of a binary tree is the deepest node which is present in the binary tree. So if you say what is the depth of this tree? So depth of binary tree is the depth of the deepest node. So here in this case, L is the deepest node because L is at the bottommost position. Okay, so what is the depth of this tree? Depth of the binary tree will be equal to depth of L, and what will be this value? Let's hop it from A to L. 1, 2, 3, 4. So the depth of this binary tree will be 4. Okay, so what is a balanced binary tree? A balanced binary tree is in balanced binary tree, if every level above the lowest is full. Okay, so suppose this is the last level of a binary tree. So if every level above the last level is complete means every node has two childrens. So suppose this is considering this example, the level above this row is this row. So if this row is complete, say B and E, C and G, okay, and so this is called balanced binary tree. This is called unbalanced binary tree because the level above the lowest is not full because Again, if you can see here, A is the root, but A does not have anything on the right, so we cannot balance. We cannot. This is a balance. This is balanced because uh, all the nodes are present at the left of the tree. There is nothing present at the right of the tree. So there is one more concept in balanced binary tree, is that the left the height of the left subtree and height of the right subtree should not be greater than 1. Okay, the difference between height of left subtree and height of right subtree should not be greater than 1. It could be equal to 0 or 1. It should not be greater than 1. So what is the height of left subtree in this case? A is the root. The height of left subtree is a height of b, which is equal to we need to go from b to I. So 1 2 2 hops. Okay, so height of left subtree is 2 1 and 2. What is the height of right subtree? Height of right subtree is also 2, because J is the deepest node, and subtree starts from C. So C to J will be covered in 2 hops, 1 and 2. So hence it is balanced binary tree, because height of left subtree and height of right subtree are equal. Now in this case, height of left subtree is height of B to I. Okay, so what is the height of height from B to I is 1 2 3 4, and but at the right there is no right subtree, so the height of right subtree is 0, and the difference between height of left subtree and height of right subtree is 4 minus 0 equal to 4, which is greater than 1. Hence this is not a balanced binary tree. So there are many ways to find whether a binary tree is balanced or not. I have just explained two ways, and this concept is very important when we solve some few problems. It is in most application a reasonably balanced binary tree is desirable. So um, binary tree will become more efficient if it is balanced. If it is not balanced, then it is as good as a linear or linked list. Because if suppose every node is at the left child, every node is at the left of the tree, then it becomes a list kind of structure. It will not become a tree kind of structure. So to make more advantages, or to take more advantage of a binary tree, make sure that your binary tree is balanced. Okay, let's cover out about what is binary search tree. Binary search tree is a special case of a binary tree where each node has two children, left and right, and the value of left children is less than the value of the parent node, and value of right children is greater than the value of parent node. So this is the property of a binary search tree, and it is very helpful while doing searches, because it reduces the number of times we need to iterate through the tree. Okay, so uh, let's see what is binary tree in picturization form. So this is a binary tree where each node has at least or at most two childrens. Yes, any node has at most two childrens. Okay, and value at the of the left child is less than the value of the parent. Yes, value of the left child is less than value of the parent. Value of the right child is greater than value of parent. Yes, value of the right child is greater than value of parent. And so there is one more important property in binary search tree, is not only the immediate nodes, but the left subtree or the right subtree is aligned according to value. So every element or every value in the left subtree will be less than 10. So here whatever value is there, however tree grows, the value at the left subtree will always be less than 10 and the value of right subtree will always be greater than 10. So this becomes kind of a balance. Okay, and how it helps to do the search we'll see just now. So also, if we traverse through a binary search tree in a particular manner, okay, we will see touch about how to traverse in a tree. But if we traverse a binary tree in a particular manner, it will always result in a sorted array or sorted form. Okay, so this is also very helpful. We will see how it is helpful to us. So binary search in a sorted array. So let's assume we have an array and say this. Okay, now look at the location of this array, which is low is the lowest element, lowest index, high is the highest index. So lowest index is 0, highest index is 6. So 0 plus 6 by 2 equal to 3. So 3, if we calculate this, we will get 3. So 0 plus 6 by 2 equal to 3. Okay. Now what is the now we divide this array into two parts, this part and this part. That is, this will become root, okay, and this will be the left subtree and this will be the right subtree. So now when we build the left subtree, how we build? Low is 0, high is 2, low plus high by 2 equal to 1. So 1 will become the child of 3, okay, left child of 3. Now let's again do one more round of iteration where low is equal to 2, high equal to 2 and low plus high equal to 2. So 2 will become the right child of 1. Okay. So using same approach, we can build this array in form of a binary search tree, which will look like this. So since we got the first element as 3, as at an index 3, so the value at index 3 will become the root. Okay, so 7 will be the root. Okay, now all the elements at the left, uh, all the element which has index less than 3, these index 0, 1, 2 will come at the left side of the tree. All the elements which has index greater than 3, that is 4, 5, 6, will come at the right side of the tree. So now we remain with this sub array, small array. Now to find a root in this sub array, we will again follow this same method, low plus high by 2. Here low will be 0, high will be 2. 0 plus 2 by 2 equal to 1. So 1 will 1 or the position at 1, which is equal to 3. This will become the left child of root node. So 3 will become the left child of root node. Again we follow the same approach, low plus high by 2. Then we get 5 will become the right child of 3, 2 will become the left child of 3. If we follow the same approach here, we will get this kind of a structure. Okay, now how this structure is helpful in searching. Suppose you want to search for 5. Okay, now we will see, now we will compare 5 with root. So 5 is less than 7. So definitely our 5 is not at the right side of 7. It will be at the left side of 7. So we will traverse left. Traversing left, what we find? We find 3. So what if we compare 5 and 3? 5 is greater than 3. That means we need to go at right, because every element at left of the tree will be less than the root element, and so we there is no way where we can find at the left side. We have to go at right side. Going right, we can find 5. So how many iterations that we need to do? We need to do 3 iterations. Let's suppose we need to find say 13. Okay. How we can find how we can find value 13? We just have to compare it with the root node. So 13 is greater than 7. Yes. So there is no way where we can find our solution at the left side of the tree. We need to go at the right side of the tree. Okay. We need to go at right side. Now going towards right side, what will be the value we got? We got 13. Yes, we find 13. So how many iterations or how many comparisons we need to do? We need to do only 2 comparisons to find 13. 1 and 2. Okay. If suppose we have to do a linear search where we just have to iterate through the list and find out a particular element, how many iterations or how many comparisons we need to do? We need to do 1, 2, 3, 4, 5, 6, at least 6 comparisons we need to do. But here in 2 comparisons we are able to find out our result. So this is how binary tree is very helpful in searching technique, because it reduces the amount of comparisons or amount of work that we need to do to search a particular element, or it will also tell whether a particular element is present or not. So for example, suppose we want to search say 15 in this, okay, whether 15 is present on this binary tree or not. We just start with root. 15 compared with 7, 15 is greater than 7, so we need to go right of the tree. Going right of the tree, we find 13. Comparing 13 with 15, we found that yes, 15 is greater than 13, so we need to go further right. Further right we found that okay, 17. 15 is less than 17, so we need to go left, towards the left of 17, but there is nothing towards left of 17. We reached till the leaf of the tree, so there is nothing at the left of 17. So that means our element that we are searching, which is 15, is not present in the tree. So we can say okay, our whatever we are trying to find is not present in the tree, and we did it with how many comparisons? 1, 2 and 3. If suppose we need to find this uh, in this array, how many comparisons we need to do? We need to do at least 1, 2, 3, 4, 5, 6, 7 comparisons, because we need to traverse till the end of the list to find out whether our uh, element is present or not. So this is how searching in binary tree works. So before going to the coding part, let's see how binary tree is represented. As we have seen in the linked list, binary tree is also represented in a structure format where this is the data part, this is the reference to the left, and this is the reference to the right. Okay, this is a very basic node structure of a binary tree. Going towards more enhanced way where we have some advanced kind of data in the data section. What we can have is we can declare one more structure called data, where we can store whatever we want. Okay, and then we can have left reference and right reference. So this is how we can represent nodes in binary tree. So let's do some problems. So this is a program where we represent binary trees. Okay, so what we are doing is here I am including stdio.h, stdlib.h. This is a structure for binary tree where we are having a data portion, reference to the left node, reference to the right node, typedefing it with tree node, so that we don't have to use struct node, and tree node is very self-explanatory. we are having a function called add node, which is just adding a node to the binary tree. Okay, so add node will return a pointer to pointer type tree node, and this will add node at, we'll be passing root here, and it will add the value to the left to the node. Okay, so how this function will work? So add node will accept three things. One is a pointer to the array. Okay, this is array pointer. One is a pointer to array. So in this program, what we are doing is we are passing an array and building a tree for the array. Okay, so this is array that I have declared, and I'm passing this entire array to the function and forming a tree for the function, and I'm adding a printf statement here that at each step what all elements we are adding, so that we can know which element is added at what preferences. So this is the left index of the array, this is the rightmost index of the array. Okay, so this is a recursive function. In binary trees, if once we should be very good in recursions, because most of the solutions or most of the problems that we do in binary tree can be solved easily by recursion. Okay, so let's begin. So first we have an exit condition. That means if left index is greater than right index, then we will exit and return null. Then we will calculate a mid equal to left index plus right index by 2. So we will get a center index, and then we will assign it as a parent or root node. So we will assign a memory here, and then we will add the values. Say we will assign extra data equal to the mid value of the array. Then we continue building the left subtree. First, how we are building left subtree? We are passing the index, what is the remaining part of the left subtree, which is left and mid minus 1. Okay, and we will build a binary left binary tree, and then we will build the right binary tree. So how we will build the right binary tree? We will build the right binary tree by passing the remaining portion at the right side of the list, like this. And now we are using this in our main function, which returns a root node, and this root node will be our primary node to work with. Okay, so this is how this program will create a binary tree and return a root node. To be more specific, this program will create, or this function will create, a binary tree out of a given array and return the root of the tree. So let's try to compile and execute this program. Okay, gcc minus o tree binary tree.c. So we got a compilation success. Let's run it. So this is how we are getting the output. First 5 is added, then 2 is added, then 1 is added, then 3 is added. So we are adding the left, first we are adding all the left portions. So first 5 is added. So what all are remaining in the left side of binary tree or left side of the array is 1 2 3 4. Okay, then 2 is added. Okay, because we pick one element as the root, so 2 is picked as one element as a root, and then left side of 2 will be added, which is 1. Then left, there is nothing on the left side of the 1. We will go whatever is the right side of the 2. So right side of the 2 is 3 and 4, so 3 and 4 will be done. So this is how we build the left tree. Then we reached 5 again because it's a recursive function. And then after once we reach the root node, we will try building whatever is the remaining at the right side of the 5. Okay, the right side of the 5 is 6 7 8 9, so we'll follow the same approach and we will end up building a binary tree. Okay, so this is our output and this is how elements will be added. Okay, let's continue. So tree traversal, what do you mean by tree traversal? So tree traversal is like how we are traversing in the tree, or how we are um, print if you want to, if somebody gives a question how to print values in the binary tree, so how you traverse the tree. Okay, so there are many ways to walk through the tree or traverse the tree. Okay, so tree traverse are naturally recursive. So uh, we whatever approach we will be following on for traversing the tree, it will be a recursive approach. Okay, since a binary tree has three parts, one is root, left, right, there are six possible ways to traverse a binary tree. So there are, what all are the ways? First we traverse the root, then we traverse the right child and left child. So left child and right child are like left subtree and right subtree. Okay, so when in the traversing terms, what if we say left, that means always a left subtree and right subtree. Okay, so here first we are traversing root, then the left subtree of the root, then the right subtree of the root. Left root right, that means first we will traverse the left subtree of the root, then root, and then right subtree of the root. So what all the combinations we can try, and this will become, this is, it depends upon what is our problem and how we want to solve the problem, and what approach or what kind of traversal technique will be good to do. So let's see three very important traversing techniques. Okay, and we will be using flag method to solve it or to traverse it. So in order, the order in which nodes are visited during the tree traversal can be determined by imagining there is a flag attached to each node as follows. So this is a pre-order, this is in order, this is post order. So pre-order means uh, first we begin with the root. Okay, in order means first we begin with left subtree of the root, then root, and then right subtree. Post order means first we uh, begin with right subtree of the root, then we come to the root, and then left subtree. To traverse to traverse in above three order, we need to collect the flags. So if we traverse this way, like try from root, start from root and start collecting flags, so we will end up in this path. We'll go from A to B, B to D, and D to E, and then A to C, F, and G. Like this path will follow. So what is this? This is a pre-order traversal where we traverse the root first and then the left subtree, then root first, then left subtree. Once it is done, then right subtree. Okay, and so pre-order is nothing but traversing the root first, then the left child, and then the right child. In order, in order is traversing the left child first, and then the root, then the right child. So this is how we do the in order traversal. We visit left subtree, we complete the left part of the tree, then we go to the root and then complete the right part of the tree. Post order traversal. In post order traversal, we complete the right part of the tree first, then we go to the root, and then we complete the left part of the tree first. Okay. So let's do some practice. write a program to create a binary tree from a given array. So this we have already completed. We just did one program which creates a binary tree from a given array. I'll advise you to try this program on your own without going to the code that I have given. In case you find any difficulty, just go back to the code, refer it, and try it on your own so that you can get more expertise. Write a program to find a specific element in a binary tree or binary search tree. So let's write this code. Let's try to solve this problem. So this is a very simple code to create a binary tree out of given array, and find a particular element in the binary search tree. Okay. So again, we are having the same kind of structure where we are having integer data and then left reference and right reference. We are having two methods. One is add node to BST, which will create the binary search tree. Okay, and we will have one function which is called find value. So this function will give us 0 or 1. If 0 is written, that means the value is not found in the binary tree, and if 1 is given or 1 is written by this function, that means value is found in binary tree. Okay, let's try to see what these functions are. So add node to the BST is a function. So this is add node to BST. This function will create a binary tree. Okay, and this is a recursive function. So whatever first we need to give a root pointer or reference to a root pointer, which is address to root pointer, and a value that what we want to add. In this function, first check if root is null, that means our tree is empty. What it will do, it will just assign or create one node, fill the value, that data part equal to val, left child equal to null, right child equal to null, assign the root to this value, like x is assigned to root. Okay, and return it. In case if root is not equal to null, then we will say if value is, or whatever value we want to add, is greater than the data part. Okay, if value is greater than the data, then we need to add the element at the right. Okay, and if the value is less than data, then we need to add the element towards the left. Okay, so here in case we found any value which is greater than the root, then what we are doing is we are again doing a recursive traversal, or we are again calling this function with the right child of the root node and adding this value to the right subtree. Okay, and in this case we are adding the value to the left subtree. So the value will be added at the leaf part, so it will keep on traversing till we found a exact condition, and then we will add the value. So in main function, how we are using is, in main function we are declaring one array. This is how the array is declared, and then we are running a loop. Okay, first we are having a root pointer declaration where we are declaring bst equal to star root, where we are declaring a pointer variable to this structure and assigning it to null, and then we are iterating through the loop and adding this value. So this is an unsorted array. Okay, and we are creating a bst out of it. So once the root is created, now what we are doing is we are using a find val function. So let's see what find val function does. Now the find val function will find a particular value in the binary tree. If a value is found, then it will return 1. If the value is not found, then it will return 0. Okay. So if the root is null, it will return 0. If value is found, like if value equal to root dot data or root arrow data, then we return 1. That means we found the value. Otherwise, what we will do, if the value is less than root data, then we will go to the left portion of the binary tree. If value is greater than, that means it will come into the else condition, then we will go to the right side of the binary tree. So this is iterative function where find val is called itself, and we will be returning some value. So where we are returning the value, if we find any element which is null, like we are traversing and we didn't find any element, we will return 0. In case if we find the element, we will return 1. And return type is equal to, we are always returning an OR value. That means if nothing is found, we will returning 0, because 0 or 0, 0 or 0 is equal to 0 only. And if something is found, we are ORing that value with 1. That means final result will be 1. So this function will return 1 when anything is found, or whatever value we want to search is found in the binary search tree. If the value is not found in the binary search tree, we will return 0. Okay. So let's see how we are using this in the main function. So in the main function, let's declare one variable int x equal to 9. Okay. Now we are declaring one more variable, say v, and calling find val function, like what if find val function is returning any value for 9 or not. We are comparing if v equal to 0, that means value is not found. If v equal to 1, then value is found. We are using a conditional operator here. Now we are again assigning x equal to 78 and saying that okay, if value is found or not. So let's try to run this program. gcc -o bst.c. Okay, we got compilation success. Let's run this program /bst. So this is the output. We have added all the values or all the elements in the array. Then we searched 9. Once we searched 9, we got 9 is found. So yes, 9 is present, 9 is found. Then 78 is not found. Yes, 78 is not there in the list, so 78 is not found. So this is how searching in binary search tree works. Again we go. So if the root is null, that means that it is not, the value is not present. If value is equal to the data present in the root, that means value is found. If value is less than whatever is data present in the root, then we need to go through left subtree. If value is greater than, that means else condition, then we need to go through the right subtree. So this will reduce our scope of search and will help us out in enhancing the search performance. So I suggest you should try this program at your own and try some different variants, like you can try out having a larger array and creating a binary tree from it, and then you can have instead of declaring whatever we want to search here, you can get value from user and do searches and all. So you can just try out and do as much as practice as you can, so that you can get more and more hands-on practice on binary search tree, because binary search tree is a very important data structure, and understanding this data structure takes some effort. It's not an easy data structure to understand. only you need to do a lot of practice to get mastery over binary search tree.
Just a quick info, guys. Intellipaat provides C and data structure training mentored by industry experts, the course link of which is given in the description below. Now, let's continue with the session.
So why sorting, or what is sorting? Sorting is arrangement of data sets in a particular order, ascending order or descending order. It all depends upon how you want to arrange. So the process of arranging is called sorting. It is estimated that 20 to 25%, 25 to 50% of computing power is used for sorting activities. So sorting is very much required or vastly used in our programs. Mainly, any complex program, if you are solving, it might require some kind of sorting. So it's good to know good sorting algorithms, and should have some hands-on practice on basic sorting algorithms. Why sorting is so much of required? Because many applications require sort. Many applications perform sorting when they don't have to. Many applications use insufficient sorting algorithm. So why it is important for us to learn sorting is, if we have a very large data set, and we are not able to sort the data in a proper manner or in a efficient manner, this could lead us to a very inefficient program, and our performance of the program will be very poor. So it is always better to apply a proper sorting technique as and when it is required. Don't apply sorting where it is not required. Apply sorting wherever it is required, and apply the proper algorithm. So some kind of applications which require sorting is examples like prepare a list of student ID, names, scores in a table for easy checking. Now this table can be sorted by ID or name. So it depends upon how we want to perform our operations. Other type could be to prepare list of scores before grade assignment. So scores can be listed in an ascending or descending order. To produce a list of horses after race sorted by finishing time for payoff calculations. To prepare an originally unsorted array for ordered binary searching. These are the just very few examples of where sorting can be applicable, but this is just four instances where sorting is used, but there are a number of instances where sorting is required, and it also depends upon your need, like whether you want sorting or not, and it depends upon your architecture, it depends upon your logic of solving your program. So it's just make sure whether our programs require sorting or not, and apply the sorting technique as and when it is required. So in this session we will be covering about three kind of sorting methods. One is selection sort, one is bubble sort, and one is quick sort. So let's start with the selection sort. So selection sort performs sorting by repeatedly putting the largest element in the unsorted portion of array to the end of this unsorted portion until the whole array is sorted. So it's very simple algorithm where it starts with a complete array, finds the largest element in the array, replaces the largest element, pushes the largest element at the end of the array, shrinks the array by one position, and then again in the next iteration tries to find out the largest element in the shrinked array, put it at the end, shrink the array again, and so on until the whole array is covered. So this is how selection sort works. So this is the algorithm of selection sort. Define an entire array as an unsorted portion of array. Okay, while unsorted portion of an array has more than one element, that means we have some elements in an unsorted array, find its largest element. Okay, swipe the largest element with the last element, reduce the unsorted portion of the array by 1. So this is a looping kind of behavior where we will be finding a largest element from the unsorted portion of the array, replacing it with the last element, and then again our array is reduced by 1. So we will be continuing this process until we don't have uh, any element in the array or any element in the unsorted portion of the array. So this is how sorting will work. Selection sort. Before sorting, this is our array. Okay. So this is our unsorted portion of the array before sorting. Okay. So after the first pass, we found that the largest element in this unsorted array is 17. So what we'll do, replace 7 by 17, like 17 is moved to the last position and we swipe with this position. So now this will become our unsorted portion. This highlighted portion will not be considered. So this will be the unsorted portion of the array. In this unsorted portion, we again find the largest element. So 14 is the largest element. We again swipe 14 with 7. So 7 comes here, 14 comes here, which reduce our unsorted portion again. So in this unsorted portion, 10 is the highest element. We replaces 10 with 3. Now in this portion, we find 7 is the highest element. We replaces 7 with 1 because the last element of unsorted portion is 1. So we replace 7 with 1 and we continue this process till we find there is no element left in the unsorted portion. So at the end we will end up in a sorted array. So this is the sorted array. If we follow this procedure, this will be the sorted array. So the code for this, very simple code. This in this code we are having we are expecting a data integer array and size of the array. Then we are declaring two variable temp and max index. We are doing a loop which is from end of the array to the 0th element of the array. Then we are assigning max index equal to 0. Now we are running one more loop which is from the first element to the rightmost, which is this one. Okay, from first element to the rightmost element. Then what we are doing is we are just comparing if the current portion is greater than the maximum portion, then we are interchanging max index equal to current. Once our this loop is completed, what we will be doing is we will be swiping the value of the max index with the rightmost element. We will be swiping the value, and this process will be keep on continuing until we exhaust it with the unsorted portion, which is represented by the outer portion of the array. Okay, so this is our array before sorting. Okay, now what we will be doing in the first portion is we will be finding the largest position in the unsorted array, which is 17. We will be replacing 17 with the last element. So 17 comes here, 7 will be replaced with 17 because 7 is the last element, 17 is the greatest element. So 17 and 7 will be replaced. Again, this will be our unsorted array or unsorted portion. What we will be doing is we will be finding the max element in the or max value in the unsorted array, which is now 14. We'll be replacing we'll be putting 14 at the end. So 14 will come here, 7 will come here. Again in this portion we'll find the max element. Now the max element is 10. We'll be putting 10 here and replaces and 3 will come to the 10th position. This will be our unsorted array now. and in this unsorted array 7 is the highest element. 7 will be pushed to the end, which is replaced by 1, and so on, so that at the end we are sorting the array in an increasing order. This is very simple example and very well known technique for sorting the array. The complexity of this program is O of n square, big O notation of n square. Why n square? Because we are running two loops here. Suppose we have an element of say size n, the maximum time that our code can take to sort the array will be equal to n square. Okay. Bubble sort. So bubble sort examines the array from start to end. Okay. Anytime it finds the largest element before the smaller element, it swipes the two. So while traversing itself, it keep on swiping. In this way, the largest element are passed towards the end. Okay, so whatever is the largest element, it keeps on swiping, and it passed towards the end. The largest element of the array therefore bubbles to the end of the array. So that is why it's called bubble sort, because every iteration we are swiping the variable or swiping the largest element, and it will be passed to the end or copied to the end portion of the array. This process is repeated until the unsorted portion of array is exhausted, or we don't have any unsorted portion of the array. So again, this is very similar to selection sort. Only thing is that it keeps on swiping the element and keeps on pushing the largest element towards the end of the array. So here's the algorithm. In bubble sort, what we are doing is defining an entire array as an unsorted array, while the unsorted portion of the array has more than one element. For each element in the unsorted portion, swipe the next neighbor if it is larger than the neighbor. So we are comparing two neighbors. Which one is the largest? We will be swiping. Okay. Suppose value at position I is say 1, and value of position I is say 10, and value of position I plus 1 is say 9. Then what we are doing is we are shuffling this or swiping the position of I and I plus 1, and so on till we find the end of the unsorted array, and we copy the unsorted portion of the array. Or sorry, we copy the largest element at the end of the array. Once the first iteration is done, we reduce our size of the unsorted array by 1, and we keep continuing this operation until and unless we are done with our array, or until and unless there is no unsorted portion is left in our array. Okay, so let's see how this works. Bubble sort. So this is our unsorted portion of the array. Now outer will represent the last index of the array, inner will represent the first index of the array. We will check whether the neighbor of whether the neighbor of inner and inner we will find the largest element between inner and inner plus 1, and then if inner value at inner portion is less than value at inner plus 1, we will swipe the value. So here we'll compare 14 and 2. 14 is greater than 2, so we'll swipe 14. Then we compare 14 with 10. 14 is greater than 10, then we'll swipe with 14. We will compare 14 with 5. 14 is greater than 5. We will swipe 14. 14 compare with 1. 14 is greater than 1. We will swipe the value. 14 compare with 3. 14 is greater. We'll swipe 14. 14 compare with 17. 17 is greater, so we'll not do again. Now our index comes to here, and then 17 compares with 7, 17 is greater, so we'll move 17 here. So at the end we have moved our largest position or the largest element to the end of the array. So 17 will come here. Now we are left with this array as the unsorted portion. Okay. Now we will again start with the unsorted portion. We'll compare 2 with 10. It's okay. 2 is less than 10, so we cannot do anything. Now 10 is compared with 5. 10 is greater, so 10 is moved here, 5 is moved here. 10 is compared with 1. uh, 10 is greater, so 1 is moved at 10's place, 10 is moved here. 10 is compared with 3. 10 is greater, 10 is moved here. 3 is moved here, 10 is moved here. 10 compared with 14. 14 is greater, so we will not continue with 10 anymore. Now again our uh, comparison portion will become 14. 14 will compare with 7. 14 is greater, so we'll swap 7 and 14. 7 will come here, 14 will come here. So this makes our unsorted portion as this one. Again we start with 2. So our unsorted portion will be this array. Again we'll continue with 2. 2 compares with 5. There won't be anything to do because 2 is less than 5. 5 compare with 1. 5 is greater, so 1 and 5 are interchanged. 5 compare with 3. 5 is greater, so 3 and 5 are interchanged. 5 compare with 10. No result. 10 compare with 7. 7 is lesser than 10, so we'll swipe 7 and 10. So we are left with this this portion is the unsorted array. And now 2 is compared with 1. 2 is greater, so we'll interchange 2 and 1. 2 compared with 3. 2 is less than 3, so we'll move ahead. 3 compare with 5. 3 is less than 5, so we'll move ahead. 5 compare with 7, so we'll not compare 5 with 7 because this is our unsorted portion. So we have ended up that we don't have to make any more comparisons. So at the end we are left with the sorted array, and this is how the bubble sorts works. Bubble sort algorithm is let's revisit the algorithm. Define an entire portion as the unsorted portion of the array. While the unsorted portion of the array has more than one element. Okay, so while the unsorted array has more than one element, this is whatever is not shadowed, like in this color, this is the unsorted portion. For each element in the unsorted portion, swipe the next neighbor for its larger next neighbor if it is larger than the neighbor. So if uh, if this current element is larger than its neighboring element, we will swipe the value. So like this we will be shuffling all the bigger values towards the right portion of the array, and we keep on doing that and reducing our unsorted portion of the array by 1, and we keep on pushing the largest element at the end, and finally we end up with the sorted array. So this is the code for bubble sort. So this is the code for bubble sort. So in bubble sort, we declared one function, or we defined one function called bubble, which accepts integer array and size of the array. Now we have one variable temp. We are running to loop. Outer equal to size minus 1, outer is greater than 0, outer minus minus, inner equal to 0, inner is less than outer. So we are running from 0 till outer. We are not considering outer. So last but one element, and inner plus plus. So if data at inner is greater than data at inner plus 1, swipe the element. Okay, so we will keep on swiping the element till data at inner is greater than data at inner plus 1. and we'll continue once the inner loop is finished. Once the inner loop is done, the largest element in the unsorted array is swiped with the last element of the array. Okay, so this is how one iteration is done. We will be keep on doing this iteration until our size of unsorted array is 0. So this is the code for bubble sort. I'd like you to try this code on your own and try to solve the problem or try to sort an array using bubble sort. This will give you more understanding on how bubble sort is used. So quicksort. Quicksort is the fastest known algorithm or fastest known sorting algorithm in practice. That is why it is named as quicksort. The average case of quicksort is O n log n. Worst case is n square. But the worst case is like it is very rare to happen. But on an average, a quicksort can sort our element in n log n time. Other algorithms that we have covered like bubble sort and selection sort, these algorithm solves the problem in n square time. So definitely n square is greater than n log n, and hence quicksort is more efficient than these sorting algorithm. And whatever other sorting algorithms are there, quicksort is the most efficient algorithm for sorting the array. So let's see how quicksort works. Quicksort works in a divide and conquer technique. So divide and conquer is a very known technique in solving or developing an algorithm. Divide and conquer majorly work in a recursive manner where we divide our solution to a smaller solution and solve the smaller solution and use the result of the smaller solution to solve the bigger solution. That is how the divide and conquer works. Any big problem divided into a smaller problem, and we solve the smaller problem, use the result to solve the big problem. So this is how the quicksort works. In quicksort, we pick any element as pivot. Okay, so we selected, suppose this is set of elements. Okay, and we have selected one pivot as v. Pivot is any element in the array. Okay, now partition S so that all the element at the left of v are less than v and all the element at the right of v are greater than v. So we have divided this array into two parts. We have selected one pivot and we have divided the array in two parts. One part has all the elements which are less than v, one part has all the elements which are greater than v, and we will solve this problem again. We will pick up one pivot from this and try to partition this array again and again. So, and we keep on doing this solution, keep on doing this divide partitioning as until we get all the partitions in a sorted manner. So conquer step is recursively sort S1 and S2. So here we divided the array in two part. Conquer will be solve this one, solve this one. So earlier what we have, what our problem is to solve this one. After division, what our problem is reduced to solving this one and this one. So we keep on dividing, until and unless our problem statements is become smaller and smaller, and once we got very small results, we'll propagate the solution upwards so that we can solve the bigger solution comparing with the result of the smaller solution. So combine the combine step, the sorted S1 followed by V followed by the sorted S2. So sorted S1 followed by V followed by sorted S2. This is our final solution. So this is the pseudocode of quicksort algorithm. So how quicksort works? Quicksort is we have an input array. Now we have a quicksort method. So and if a left is less than right, that means we have a valid condition. We'll select one pivot uh, and we'll partition our array, or we'll partition our array with the pivot. So we have two portions. One is left as left index and pivot minus one. One is left as pivot plus one and the right index. And we perform quicksort on these left portion and then quicksort on right portion. So this is a recursive approach where we are keep on solving this. We are keep on dividing the solution till we reach some position where we have only single portion, and there is nothing to solve in a single element or single portion, so we propagate it up and solve it. So this is how pictorially we can represent quicksort, how it solves. Assume this is a bigger set. We select one pivot element, say 65, and we divide our array into two portion. One portion is less than 65, one portion is greater than 65. We solve this smaller portion and combine the solution of the this smaller portion to get final result, which where our entire array is sorted. So let's write some code for quicksort. Let's try to solve or write a program to see how quicksort works. So let's write some code to understand how quicksort works. So this is a program how quicksort works. I have written two methods. One is a method called quicksort, which actually performs quicksort. One is a method partition, which partitions our array for a given pivot value. Okay, so let's see how quicksort works. So this is how quicksort method is looks like. So I have taken two variable p and r. P is a starting position, r is the pivot value or end position. We are in this example we are considering pivot as the last element of the array. So this is our exit condition. If p is greater than r, then we are returning. Then we are calling partition method, which will partition our array from start to the end element, where end element is the pivot. This is how partition method works. So we are having two variables, I equal to p minus 1, j equal to p, and temp and temporary variable. We are running a loop where from j till r, where until j is less than r. If at any point of time a of j is less than a of r, we will be swiping the value. We will be incrementing I and swiping the value of I and j. Okay. Once we are done with this loop, we will be swiping the value of I with r, incrementing the I and return. So I will be our partition. Value from p to I minus 1 will be partitioned, and value from I plus 1 to r will be partitioned, and I will be placed at the correct position. Okay, so here the partition method returns an integer or the correct index of our pivot, and then we call quicksort method in a recursive manner to sort our array from p to part minus 1, and subsequently calling quicksort to sort the part plus 1 to r. So this is our left portion, this is our right portion. So the part, whatever the value which is written by a partition function, will be the correct position of a pivot in an array when we sort the array. So we this part position divided the array in two parts. one part, like this part will be having all the value which is less than the element at this position, and this part will be having that, like part plus 1 till r will be having all the values which is greater than the pivot element, and so on. We will be continuing iteratively, and uh, ultimately we will be sorting the array. So in main method, what I am doing is I am declaring an integer variable, integer array of size 10. You can see this is an unsorted array. Okay, we are calling quick sort, where we are giving the array 0th position and the end position of the array. So this quick sort method will sort our entire array, and then we are printing our sorted array. Okay, so let's try to compile and run the program. Compilation is successful. Let's try to run it. So we are getting an array in a sorted order. So let's revisit the program again. We have two functions, quick sort and partition. Will perform quick sort on the partitioned array. So partition method will do nothing but partition or array, or give an index which partition or array in two halves. One half is less than one half has all the elements less than pivot, one half has all the element greater than pivot. Once we get this index, what we are doing is we are again performing quick sort on the remaining halves, which is equal to start and part minus 1, part plus 1, and r. So this is how we can solve quick sort using divide and conquer approach. And this is divide and conquer approach is very helpful in these kind of techniques. Okay, so this brings us to the end of this session. I hope you understand a lot about sorting and different type of sorting techniques.
Just a quick info, guys. Intellipaat provides C and data structure training mentored by industry experts, the course link of which is given in the description below.